Hi, good morning, and thank you for joining us today. I'm the MC, Phoebe. So before the distinguished lecture starts, may I invite all of you to first rename your Zoom display name to Name Analysis Institute to facilitate today's discussion. Second, use chat and raise hand functions for posting questions during the talk. Third, mute your microphones when not speaking. And fourth, there will be a group photo screenshot, and please feel free to use the background we have provided. Now let's invite Professor Kenneth Leung to give us the opening remarks and introduction of the SKLMP Distinguished Lecture Series. Welcome.
Oh, thank you, Phoebe. On behalf of the City University of Hong Kong, the State Key Lab of Marine Pollution, and the Department of Chemistry, I offer my warmest welcome to all of you. Up to now, we have 90 participants joining this talk. We are expecting more people to come. The rationale behind of this distinguished lecture series is that I can use a Chinese phrase to explain this. In Chinese, we say, 聽君一席話，勝讀十年書. The translation is that listening the words of a wise man can be superior to studying 10 years of books. So today we're going to read books more than 10 years from Jerry. So we are very happy to have Professor Gerald Schnell to share with us about this global challenge on climate change and the ocean. So before the MC to introduce Jerry and also his talk, I'm going to spend just 1 to 2 minutes to talk about our State Key Laboratory of Marine Pollution. If you can turn to the speaker mode, you can see my background. Then you can see the TREE, the tree, actually referring to our research area. The T means technology. We aim to develop innovative technology for pollution monitoring and also control. Then the second one, R, referring to risk. That means the risk of chemicals to the environment and also to human health. Then based on our research, we can tell you how much chemicals in your seafood is not okay, how much chemicals in the water, in the seawater, is safe for swimming. So we are working on this area. Final one is called E&E, means ecosystem response to pollution and ecological restoration. So we also want to understand how pollutants are affecting the ecosystem and how can we clean up and restore the ecosystem using new technology. So those are 3 main areas of our research. Hopefully you remember the tree in the sea is our State Key Lab. Then the second things I want to share is the next next distinguished speaker is Dr. Janice Stapa. She is one of the academicians in Australian Academy of Science. May I invite Jenny to say hi to everyone?
Thanks, Kenny. Hi, everyone. I'm delighted to be here today, and I'm looking forward to talking with you in May on a topic yet to be decided, but likely to be deep sea environments and particularly mining impacts of deep sea tailings placement.
Wow, that is a very interesting and important topic. Thank you, Jenny. So finally, before I pass over to Phoebe, I would like to congratulate Jerry again for receiving very, very prestigious award for his outstanding achievement in environmental science and technology by the American Chemical Society and the flagship journal, Environmental Science and Technology. Jerry was the chief editor before, and also he was the founding editor of ES&T Letters, which is a really, really successful journal too. So without further ado, I will hand over to Phoebe. Once again, thank you everyone, especially Jerry, for presenting his talk today. Thank you very much.
Thank you, Professor Leung. Now, Jill, please open your camera for taking a group photo. And then Professor Schnoor, could you please stop sharing your screen so as to take a group photo? Thank you.
Please, everyone, turn on your camera so that we can see your face.
So are you there? Are we ready? Hello, Sora, are you ready?
Yes, I'm okay. So, ready, 1, 2, 3. And the next page, ready, 1, 2, 3. The third page, ready, 1, 2, 3. And the last page, ready, 1, 2, 3. Thank you. We're done. Thank you.
Okay, thank you, Sora, and thank you all. Now, before my introduction of the speaker, may I once again remind you that first, to mute your microphones when not speaking, and second, use chat box and raise hand functions for posting any question during the talk. Okay, now let me introduce our speaker, Professor Gerald Schnell. He is the A.S. Henry Chair in Engineering, Professor of Civil and Environmental Engineering, Professor of Occupational and Environmental Health, and co-director of the Center for Global and Regional Environmental Research at the University of Iowa, USA. Professor Schnell's research interests include phytoremediation, water sustainability, and climate change. He is a member of the U.S. National Academy of Engineering, elected in 1999 for research and engineering leadership in development, validation, and utilization of mathematical models for global environmental decision-making. Professor Schnoor served as editor-in-chief of Environmental Science and Technology from 2002 to 2014, and as the founding editor-in-chief of ES&T Letters from 2012 to 2014. Today, Professor Schnoor will tell us about climate change and the sea. So let's welcome.
Thank you, Phoebe, and thank you, Professor Leung, for inviting me. It's indeed a privilege and an honor. I've really enjoyed my association with SKLMP, and I hope you'll still have me in the future. I'm going to try to share my slides now. We've had some trouble making it full screen, but let's see if it works. Is that full screen for you?
Yes, yes.
Okay, good. Climate change in the sea. I hoped to concentrate on marine environment with respect to climate change, because I know in Hong Kong and China, you're very interested in that. And I too became quite fascinated by how climate change has affected the sea. Now it won't advance. Let me see. This is the planet Earth that we're trying to protect, and The warming associated with climate change is a top-down warming. The very thin veneer of atmosphere, less than 50 miles high, held to the Earth by gravity, is a very small reservoir. And it's the first one on a mass basis that we should affect when we have nearly 8 billion people and a gross world product of almost $100 trillion each year. And indeed, that has been what happened. We added greenhouse gases to the atmosphere, and like putting a blanket around the atmosphere, we began to warm the atmosphere, which then warmed the sea, our subject today. And more than 70% of the Earth is covered by the oceans, and it's the biggest thermal mass. In fact, if you want to go where the heat has accumulated, you should go to the oceans. And in fact, 91% of the extra heat from global warming resides in the oceans. More about that later. The sea then is very important for everything from commerce to ecosystem function and structure, and even the balance of oxygen by photosynthesis on Earth. You may know that last September, I believe, was a new report issued by the IPCC, the Intergovernmental Panel on Climate Change, called AR6. It's the 6th report in a series from 1990. Each report became stronger and stronger, and the certainty of the findings more and more highly statistically certain. And now words are like, it is unequivocal that human influence has warmed the atmosphere, the ocean, and the land. Widespread changes throughout the ocean and the cryosphere. In fact, the changes that we've seen in carbon dioxide have not been seen on planet Earth for at least 2 million years. I think many more. Has it never been so high as today? And for methane and nitrous oxide, at least 800,000 years. It's never been so high as today. As you know, the problem is that the red arrows burning fossil fuels that took, in the case of coal, 340 million years to form, and burning them up in a couple hundred years is this red arrow. And this red arrow has to do with emissions from land use change, clearing of forests, like in the Amazon, and the burning, biomass burning. Those two red arrows are quite a bit bigger than the two black arrows, which is carbon dioxide going into the forests and soils and going into the oceans, such that we end up with excess in our, really it's our exhaust pipe, if you will, in the atmosphere of about 16 billion metric tons, gigatons of carbon dioxide each and every year. Because CO2 is a trace gas, it wouldn't matter very much, except that it's a radiatively important trace gas. And infrared radiation, it's opaque to that and warms the atmosphere. The CO2 is now about 415 parts per million. We started in pre-industrial days at 280 parts per million, and it just continues to go up exponentially with both with population, but even more importantly, with per capita consumption as we develop. When you have greenhouse gases accumulating in the atmosphere, that means that it's going to change the energy balance of the Earth and warm the Earth. And indeed, the signal emerged from the noise in about 1970. The decade of the 70s were warmer than before, the 80s more, the 90s more, and so on, such that we are really experiencing now a clear-cut signal of warming due to this accumulation of greenhouse gases. Now, we launched a series internationally. We launched a series of satellites, the Ceres satellites, in order to try to understand the Earth's energy balance from the atmospheric standpoint. But it's very difficult to do. The mathematicians would call it a ill-conditioned calculation, because we're looking for the difference between two large numbers. The large number going in is the solar radiation of 340 watts per square meter. And then the back radiation, or infrared radiation, is 239 plus reflected infrared, plus reflected solar radiation of 100. So 340 coming in and maybe 339 going out. Just 1 watt per square meter is what we're talking about, causing the whole problem. It doesn't sound like very much, but we'll see that it is. The case for human-induced climate change, we scarcely need to talk about any longer, because it's much like a lawyer laying out their case, layer upon layer of multiple lines of scientific evidence. Evidence from the Earth-based stations, from satellites, from ice cores, down borehole measurements into wells, ice core data and proxies, energy spectral changes, fossils and tree rings, on and on and on. Even the pattern of warming is unique to what has happened. And that is, we have colder temperatures in the stratosphere, warmer temperatures in the atmosphere below where the greenhouse gases warm the Earth, and also warmer temperatures in the higher and lower latitudes. For example, in the Arctic, the ice begins to melt, the floating ice, and the white reflective surface yields a dark sea, which absorbs more radiation, making it warmer in a positive feedback loop. The more the ice recedes, the darker the sea, the more the radiation is captured and warms. Now, ever since we were born, and ever since the Industrial Revolution, emissions have continued to increase. There was a small pause during the pandemic, and then actually in the past year, it's gone back up again to record levels of about 38 gigatons of carbon dioxide each and every year being emitted. But what we need to stabilize the climate and to stabilize the chemistry of the atmosphere is this blue line going sharply down for a 50% decline by 2030 and net zero by 2050. That's a very big challenge. As we said, that carbon dioxide is the major contributor, but there's many greenhouse gases. And two that I'd like to focus on for a moment is methane, which is about 17% of the radiative effect, and black carbon, soot, which is about 20%. The reason I'd like to focus on those is because they're, to me, an opportunity. We say low-hanging fruit, where we should begin to try to stabilize our energy balance right away. Methane has only a 12-year half-life in the atmosphere, so it's rather short-lived. If we could begin to control all the sources of methane, we would get an immediate reduction in warming. And likewise for black carbon, just very short residence time in the atmosphere. We should be controlling it anyway for human health reasons, and we could get an immediate benefit from that. We're not sure why methane is increasing so rapidly in the atmosphere. In fact, I remember teaching my students in the 2000s oh, good, it looks like it's leveled off, the methane concentration. But now again, up, up, up faster than ever. I believe it has to do with the more and more natural gas and oil exploration, and especially fracking operations. When we fly an infrared instrument over Texas, for example, here in the United States, it's just a big cloud of greenhouse gases as you look down. But also it could have to do with the positive feedback of permafrost melting and clathrate methane ice beginning to evaporate into the atmosphere. That would be very bad. Of course, we have almost 8 billion people, and that means we have more animals and more manure, which cause anaerobic digestion when we move it around, and that causes more methane. And yes, with more people, we need more agriculture and more rice and wetlands, and that also means more methane. I'm pleased to mention that one of my former students, Marcelo Mena, has been named head of the Methane Hub, a $340 million operation, an NGO, with now 111 countries signed up to try to control this problem, which indeed would help us with our global warming quite rapidly. Likewise, black carbon, the lighter aerosol particles reflect solar radiation back into space, but the dark particles absorb it and add to the problem of global warming. And this should be something we should be controlling anyway for human health reasons. But it has to do with everything from cook stoves to burning of coal. Biomass burning is a problem here also, and diesel motors. Many cars in Europe are still diesel. This we should be able to control, and it should allow us to improve the situation quite rapidly. I mentioned at the outset that if you want to know where the extra heat is, you should go where the heat capacity is greatest, and that's in the ocean. More than 90% of the heat resides in the ocean. Ever since 2005 international experiment that our countries are involved in, we've had the Argo program. We're now over 4,000 SONs, measuring devices in the ocean, floating freely. In fact, you can see at any time where they are online. They come up to the surface to recharge their batteries with solar insulation and go through a programmed dive of about 7 to 10 days. Originally, we sent them 2,000 meters. Now we're sending them 6,000 meters deep because we can see the heat signal top down that deep as 6,000 meters. Again, it looks like it's about close to 1 watt per square meter that I mentioned earlier. This is the Noaa analysis of the data, and we're now up to around 20 times 10 to the 22 joules of extra heat. I have my students try to put that into some perspective. The Hiroshima bomb, which sadly was dropped at the end of World War II, released about 63 times 10 to the 12, 63 trillion joules of energy. If we had such a bomb going off 7 times every second, 24 hours a day, 365 days a year, that would be equivalent to the heat that we're adding to the oceans every year. So while 1 watt per square meter may not sound like a lot of heat, it really is a tremendous amount of heat, which is now part of the content of the oceans. And after we stabilize the atmosphere, it will take time to release that heat and cool back off again. The global warming, as you know, is about 1.1 degrees Celsius so far. Oh, what happened? Sorry. about 1.1 degrees Celsius so far. And you can see here in Hong Kong, the seas are about average. They're about 0.9 degree, the open ocean. The sea surface temperature is about 0.9 degrees Celsius warmer. And South China also is roughly average temperature of about 1.1 degrees Celsius warmer than pre-industrial. Of course, when you have warmer seas, we don't think that the number of typhoons, tropical cyclones increases, but the typhoons that we have are much stronger, Category 4 and Category 5 storms. Also, what seems to be occurring is much larger storms, almost continental size storms, as you can see here, and in the eye, lower pressures than we've ever experienced before. And this was the terrible Typhoon Haiyan in the Philippines in 2013. Over 7,000 people died. Terrible, massive storm, winds of 195 miles per hour, and the lowest pressure ever measured in the Pacific, 895 millibars. Of course, it was followed, as you know, just this last December by Typhoon Rai, not quite as big, but also 160 mile per hour winds, a Category 5 storm, and many, many deaths. So the number of typhoons don't seem to be increasing, but the very serious ones are being fueled by warmer sea temperatures. About 1 degree Celsius is enough. These storms were roughly fueled by seas of 31, 32 degrees Celsius water. Very warm. Of course, Hong Kong is vulnerable to climate change. Also, Hong Kong is almost unique for this population with 733 kilometers of coastline, which makes it very vulnerable to floods and landslides. And of course, the precipitation is among the highest locations in such densely populated area, with now up to 3,000 millimeters of rain. And the serious storms, I've been there. I remember with Shandong Li in a storm where all the tunnels flooded, and I know how difficult it is to get around in those situations. You already have invested large amounts of money in underground storage tanks. They have helped the city a great deal, but probably more needs to be done in the future. When you have when you have warmer temperatures, of course, ice begins to melt, and especially the ice that is up on the land is a serious problem for adding to sea level rise. Here we see the Greenland ice sheet, and one of my dear friends from Eawag, Connie Stefan, who invited me, this is Connie right here, who invited me to go to the so-called Swiss camp each and every summer. He made the first measurements on the quantity of meltwater shown here in Greenland. Connie actually fell in December 2 years ago and lost his life as a result of these early measurements. And it's actually, the amount of water is equivalent to roughly half of Lake Erie each and every year running off Greenland into the sea. And that now represents the glacier melt worldwide, represents about 50% of the sea level rise that we're experiencing. But the worry here is especially, this is a shaft, they call it a mula, and this shaft carries the meltwater down to the surface between the land and the ice sheet base. And we worry about the lubrication effect of the glacial ice, which is floating off the island, off Greenland by gravity, moving off much faster as a result of this lubrication. In Western Antarctic, there's even more ice, enough to, if this area right here, which is very vulnerable at the moment, Pine Island and Thwaites, is about to fall into the ocean. That if the entire ice sheet went, it would raise sea level 3.3 meters in abrupt climate change. So in the previous IPCC reports, the previous 5 reports, they wouldn't even talk about abrupt climate change. But now for the first time, they try to do that. You know, as humans, we don't deal very well when the consequences are infinite, but the probability is near 0. What do you get when you multiply 0 times infinity? It's undefined. We don't even know how to deal with that. And so scientifically, it's still a problem of how we even talk about abrupt climate change. If it happened, it would be awful. You can see the effects on the Indian Ocean, Bangladesh, and India and Pakistan. Of course, the Bohai Sea and the Yellow Sea. Many people, millions of people would be inundated in the worst case. And even in Hong Kong, you can see many problems as a result. Florida, in my country, you can forget about that seaside property that you were thinking about buying. It would be under. So these tipping points are a concern, and they're finally addressed in the AR6 report. Abrupt changes in ocean circulation, such as shown here with the Gulf Stream, which warms Europe. Coral reef die-off, ice sheet collapse, which we mentioned, shifts in monsoons, permafrost melting and release of, in a positive feedback loop, release of methane. And yes, even the models don't do well in predicting El Nino and La Nina, but the frequency and magnitude seems to be affected by climate change. About all we can do as scientists is put what we know into a model to try to make a projection, is what we call it. And there's various scenarios of how society will deal with this problem out to 2100. And it seems that we're following kind of this middle ground here, SSP2 4.5 in the AR6 report. And that would result in our, remember, we're already warmer, about 1.1 degrees Celsius here on the y-axis. So we're talking about experiencing in our kids and our children's lifetime more than 2 times that, maybe 2.5 degrees Celsius, based on what is happening right now. Sea level rise, for the first time in the AR6 report, they begin to talk about abrupt climate change of the kind of collapse of ice sheets that I showed you. And this is the new line. If things really happen badly. Again, we're following rather this kind of not worst case, but not best case either, this kind of in-between pathway. And it says that pH of oceans will change from about 8.05 to about 7.9, continuously getting more and more acidic. Based on the models, this is the y-axis here is the change in warming averaged over the whole Earth. And we'd like to, the United Nations says, we'd like to control it at 1.5, no higher than that. We're at 1.1 right now. And this blue area means that we can only continue to burn fossil fuels for about 8 more years only. And then we will exceed the 1.5 degrees Celsius and continue up as I mentioned earlier. One of the things that I'm very interested in, because of one of my mentors was Werner Stumm at EOLOG in Switzerland, and we talked a lot about what's the PE of the sea? What's the redox potential of the atmosphere? What's the redox potential of the sea? And you realize right away that all these master variables that affect every physical, chemical, and biological reaction, all of these master variables are changing. Temperature is probably most important. I would put pH second, salinity third, and ORP is quite interesting too, or the negative logarithm of the electron activity. It's represented by a massive disruption in the redox and the acid-base balance of the Earth that goes along with this temperature anomaly. I like to express it like this: the land, which had millions of years of forming dense vegetation into coal, oil, and natural gas, represents a reservoir of reduced compounds, carbon, sulfur, nitrogen, which when you mine them and burn them, uses up oxygen in the atmosphere. And by the way, at Cape Grim in Tasmania in Australia, we can see the signal, even though oxygen is a major gas and CO2 is a trace gas, we can see oxygen decreasing at Cape Grim. So we are consuming oxygen out of the atmosphere and producing these oxidized chemicals, CO2, sulfuric acid, nitric acid, and acidity. And the CO2, the weak acid, which is the highest in concentration of those, undergoes mass transfer to change the oceans. So it's really a massive disruption in elemental cycles due to 8 billion humans and $100 trillion a year gross world product, which changes the solubility, the acid-base balance, the redox, and even the oxygen concentration in the entire ocean. Now, Stumm taught me that the PE of the sea is balanced most strongly by this reaction. Oxygen is dominant in oxidizing a wide variety of photosynthetic products in the ocean. We get about 42 moles, about 42 electron equivalents per square meter per year of photosynthesis each year, which is driving the PE of the sea with this half reaction and many, many reductants to be oxidized. That means that the dissolved oxygen in the oceans are declining because of, partly due to the increased ocean temperature. That's about 15% of the reduction, but mostly due to the change in the oxygen supply from, again, we can tell from the Argo program, from changes in the ocean stratification and changes in the deep sea microbial respiration. Thus, this is the y-axis is in percent decline of ocean, open ocean dissolved oxygen concentrations, and you can see as they're coming down. One of the surveys, this is now more than 10 years old, but open ocean dissolved oxygen concentrations between 200 and 600 meters. This is not nearshore pollution we're talking about. We're talking about open ocean oxygen concentrations are in the deep red here, less than 100 micromoles per kilogram. The average is 162 micromoles of oxygen per kilogram. So this is quite a bit lower in the pink areas. And in the dark red areas, it's less than 20 micromoles per kilogram in a wide swath of the ocean, 200 to 600 meters deep. A lot of these effects, especially the temperature effect, master variable, and the hydrogen ion acidity, master variable, are causing the coral reef decline, in addition to pollution and several other causes. We already know that some coral reefs are losing calcium carbonate faster than they can form it. They form it in the form of aragonite, and the saturation state of aragonite is decreasing. Thus, the coral reefs are in danger of basically dissolving on a net basis. We're losing species because of this. And worldwide, it's about 1 million species to extinction. Now, we don't know how many species we have. There's only Latin genus and species names for about 1.4 million. But the best estimates using actually artificial intelligence is that we have about 8.7 million species. So to lose 1 million in our lifetimes is really incredible. I tell my students it's not like Jurassic Park. We're not saving these genomes. We can't bring them back. Once they're gone, they're gone. It's irreversible. And the extinction rate is roughly 100 to 1,000 times natural. 50% of the problem is in the marine area that SKLMP is so dedicated to. And ocean acidification and coral reef collapse is a very significant part of the problem. Some of the species, as you know, amphibians, reptiles, fishes. This is a famous one that was wiped out in Japan, the orange-spotted filefish, and other famous organisms like polar bears and large penguins, Adelie penguins. One of my heroes died last year. He was E.O. Wilson, Harvard biologist and naturalist. And he wrote the book, maybe you've read it, Half Earth, that we need to preserve and dedicate half of the earth and half of the oceans if we want to solve this problem. And it's not as bad, it's not as difficult as you might think, because in Wilson's book, he lays out how we can put corridors together on land of corridors of rivers and streams, hooking together with national parks and pristine areas like the Amazon, and really begin to try to preserve terrestrial species. And for the marine species, we need to make many more marine parks, protected zones for saving the oceans. I've gone to almost every one of these meetings ever since 1992 and the Rio Earth Summit. Because of the pandemic, I did not go to the Glasgow meeting last November, but at least somebody is talking about these problems and how we might form an alliance, much like the Montreal Protocol, which was very successful for the freon chemicals and the stratospheric ozone problem. And these are the crucial issues that are being discussed. Again, some of the successes, I would say, is this global methane pledge. I believe we're really going to try to level off the increase in methane, and some of the carbon market and international trading systems also could really help. Most people at Glasgow believe that we need to electrify almost everything. Electrification of the cars, electrification of all our appliances. We need to use mostly renewable power like wind and solar and ocean power. And nuclear also needs to be a part of the baseline mix. And we need to decide how we're going to dispose in deep geologic repositories the nuclear wastes. Electric vehicles, battery storage is coming on strong. Vehicle to grid. In the United States, we have 240 million cars. If you take 240 million cars and put storage batteries in all of them, it becomes a tremendous battery storage resource. Over 600 gigawatts of energy in those batteries, and that has to be in a modern grid with public charging stations so that our cars will both feed into the electricity grid as well as take from the grid. We need to price it when at night when people aren't using power. We need to make the price low so that we can do things like hydrogen production and utilization. And all of this really, to my students, I tell them, this is going to be the engine of economic growth for the future, for you and for your kids. Millions and millions of high quality jobs. It's clear that we need to put a price on carbon. In the US, we still have not done so, except in a few locations, the northeastern US and California. We have a national proposal to do that, a fee and dividend in which you put a price of carbon at the wellhead or the port of entry. And that makes fossil fuels very expensive so that people won't use them so much. And it allows economies of scale for renewable energy to grow and become cheaper and cheaper. It's designed to be revenue neutral such that the taxes that are collected will be distributed directly back to the people, each and every individual. People who use little amounts of fossil fuels will benefit, make money out of this proposition, and people who use a lot, about 30% of our country, will pay much more for the fossil fuels. You know, what we're talking about is a very good thing. The air will be cleaner, health will improve. I testified before Congress in the US about the Harvard 6 Cities study, and that for every 1 microgram per cubic meter of decrease in fine particulate matter, we save 750,000 lives. We need to lose at least 10 micrograms per cubic meter in my country. That's almost 1 million lives each and every single year. Due to when the particles go up in the air, people check into the hospitals and they don't come back out. It's about 50% deaths due to heart disease and 50% deaths due to pulmonary emphysema, asthma, and so forth. There'll be fewer heat strokes, fewer disease vectors and mosquitoes, and no more smog, if you can imagine. So I leave you with the idea of which model is correct. These are all the realizations of the models that we're running, even in my center. And I think we're basically following these orange, yellow ones here, which I'm sorry to say will leave us with about 2.5 degrees Celsius warmer, more than the 1.1 degree Celsius right now. I have hopes and prayers that we can emerge more in these blue realizations and control this problem much, much earlier for our children and our children's children. There's lots of good things happening. There's lots of climate action already with renewable. Imagine if all the energy was free. No more do we have to fight wars over fossil fuels. Free fuel into the entire future. No one owns the sun and no one owns the wind. And high quality jobs in manufacturing and infrastructure, cleaner air, better health, public benefits. And we're doing it, but we're not doing it fast enough. That's the message. We need to move faster, accelerate this program, and it'll be a much, much better world that we'll achieve for us, yes, for the oceans, and for all the other species. And one of greater social justice and social equity as well. You're very kind to invite me, Professor Lung. Thank you so much. If there is time, I'm happy to try to answer any questions. Thank you.
Thank you very much, Professor Schnoor, for giving us a wonderful talk. Now comes to the Q&A section.
I will stop sharing.
Yes, thank you.
Could I start by asking a question, please? It's Janice Stapa here. Lovely photo, Jerry, of the Sydney Opera House and Harbour Bridge with a brief last slide from my hometown. What I wanted to ask was, the IPCC reports have been very quiet on the interactions between the climate change stresses that you very nicely outlined and chemicals and contaminants. So we've got these multiple stresses. We've got climate change stresses and we've got our chemical pollutants, and they're interacting in many different ways to change tipping points and affecting processes. Is there a way we can better get that interaction and get the climate scientists more involved in the ecotoxicology, you know, the risk assessment of the chemicals and vice versa than what we've been currently doing? Because we've been quite unsuccessful in getting chemical stresses as part of that climate change story so far. So any suggestions?
You raise a wonderful point, Jenny, and it's true. There, I know from participating in the IPCC reports, there's almost next to zero ecotoxicologists, and so I think you actually suggested the solution is we need to change that, and maybe scientists like yourself and me too. We need to try to stress the importance of these interactions. You'll notice that I mentioned on the coral reef collapse that, you know, there's many stressors, and I realize pollution and nutrients is certainly one of the biggest ones, not just climate change, although that was our talk today. But you're right, the interactions are many and ripe and not that well understood, I would say, either. Thank you for that comment.
Thank you.
Professor Chen, please.
Hi, good morning, Professor Schnoor. I have a question. Of course, we know that the pandemic changes almost everything. And I reckon that, you know, with more mass disposed and perhaps a lot of plastic bags because of, you know, more to go, Dina. Maybe there may be microplastics, things like that, more in the ocean. But I would like to ask you, do you know what impacts the COVID pandemic has made related to the maybe the redox activity and some of the more chemistry aspects in the ocean? Thank you.
Thank you, Professor Chen, for that question. I confess I don't know. I did see one paper about the pandemic and the masks, which is a huge problem, as you know, and people are trying to address what is happening to all the masks, and many of them are blowing around on the land and into the sea. But the microplastics and the other questions, it raises sort of what Jenny asked too, that, you know, the interactions of all of these things, more and more commerce, more and more plastics production, and how do we account for that? Eddie Zeng and I just wrote a paper. Really, Eddie wrote it and he allowed me to read it on the e-waste. And China has done actually quite a remarkable job in just the last 15 years with new laws and extended producer responsibility in handling the e-waste better. And I don't know if that addresses your question, but I think you raise an important point.
Thank you.
Professor Eddie Zhang, please.
Me, Jerry, thank you very much for your informative seminar. I think I learned quite a bit from your presentation. Okay, I really appreciate all the new strategies and ideas you just mentioned to reduce carbon dioxide emission. I'm thinking, you know, maybe we can look at the other way. Can we create and maintain some long-term carbon reservoirs? For example, we've been talking about producing bio-based plastic, which can be, you know, taken from atmosphere. You know, a lot of the CO2 can be transferred into plants, and then we can use plant to produce, you know, bio-based plastic. And another thing is can we find a way to store all the existing plastic? So the carbon or carbon dioxide can be stored for a long time. So instead of just working one way, can we create another reverse way to kind of reduce the carbon dioxide from the atmosphere? Do you have any comments on that?
It's another great question, Eddie. The one that you hear about the most, as you know, is sinking these things. Even when we reforest with trees, you know, maybe they grow for 100 years and then they reach their climax and we have to cut them and get rid of them somehow. In my group, we're making biochar out of them, and that lasts maybe 100 years in the soil as a soil conditioning agent. That's just one idea. But as you know, other people have talked about sinking them into the ocean deep, and plastics also could be put deep into the ocean such that they wouldn't come back for thousands of years. And that's about the only solution I've heard, but I would open it up to our listeners because, you know, there's probably some other good ideas out there.
Thank you. Very good.
Thank you.
So, Jerry, I have a question. Why now many countries trying to build those carbon dioxide storage system, just like in Iceland? Would this be a way forward to cut down the CO2 footprint? And my second question is trying to ask on behalf of some school kids here. So what can we do as a citizen to help or combat this climate change issue from the individual point of view? What can we do? Thank you very much.
First one with Iceland, as you know, it's kind of a unique situation. They're blessed with so much hydropower and then geothermal besides. So I think they have a wonderful possibility to work on removing carbon dioxide from the atmosphere directly, as you refer. They're also trying to create a hydrogen economy because they have so much renewable power. They can even just use electrolysis to make green hydrogen. So Iceland is sort of a unique place, but I'm happy that there's still research going on about removing the CO2 directly from the atmosphere, but I myself, and in my research, I'm much more interested in using reforestation on marginal lands in the Sahel, in the Mongolian desert of north and west of China, in the Gobi Desert, north and west of China. This is what we should be doing immediately, and it's rather low cost. Eddie Zeng's question, then when it reaches a climax, you have to replant again and do something with that wood, and I would turn it into would be my suggestion.
Mm-hmm. How about the second question as just the children or ourselves as a citizen, what can we do?
Well, I think everybody has to take it upon themselves to make their own carbon footprint smaller too. So obviously we can weatherize our homes, we can change our diets and just maybe eat less meat and more grain. We can do things like planting trees. We can buy electric vehicles and urge our countries to use renewable energy rather than fossil energy to fuel the cars. So I think there's a lot to do. One of the things when my students ask that question, I tell them, you know, you need to vote for the people who believe this is a serious problem. That's one of the most important things you can do as an individual.
No chum.
Yes.
So any questions from the audience? Professor Xiangdong, would you like to give some comments or questions? Or Professor Noaa as well?
Hi, Jerry, and it's a great talk. And I think you have a very good point, kind of like both scientifically discovery and how individual and we can help in a really strategic goal. But my point is we saw quite a successful CFC, like ozone depletion task, which actually identified and have a kind of a really great joint effort from private sector, from government side. But regarding for this climate change issue, we have been aware and we have been IPCC report. We have a kind of a very much debate, but the progress is alarmingly slow. And so I thinking is innocent from our scientific community, or even you already mentioned about from our model citizen, how we can contribute at home, at work. So what is from your views, really kind of the problem and difficulties hinder us to looking for so efficient, effective measure to do is even larger than the ozone hole problem. Jerry, I need some of your will and advice on this.
As I tried to say, I'm actually an optimist. I believe that we are going to address this. It may get quite a bit warmer before we are successful and many of the effects we talked about are reversible, not the loss of species, that's irreversible, but many of the others are reversible. So I think everyone will eventually realize as things get warmer, get worse, that this is very serious, and we can prosper, as I said, from this. It is the way to prosper in the future. So I'm rather optimistic. I think it will get worse before it gets better. But I think that what the missing part of your question is the economic signal, the price. The fossil fuels are not paying all the externalities for the healthcare, emphysema, asthma at record at levels, for all the deaths I talked about from the fine particles, PM 2.5, from the lost time of people not being able to work, from the corrosion and the materials damage of the acidic pollutants. None of these costs are being paid. It's a failure of the capitalist system. It has failed us. And therefore, we have to send a price signal into the marketplace to make those, if not pay their true cost. My students think that a gallon of gasoline should be at least $20 a gallon. If they can't pay the true cost, then we have to at least move it that direction. And at the same time, with economies of scale, that'll make renewable power even much, much cheaper. So I think that's the real missing thing, is the price. And capitalism has failed us.
Thank you.
It's a market failure.
Thank you. I invite Professor Jiang Guibing to give some comment or question, please. Professor Jiang.
Okay, thank you. Hi, Jerry. Congratulations for your nice talk. During the past year, I do the same. We talk about the carbon neutralizations. I understand the total discharge of carbon dioxide on average developed country like US, the average carbon dioxide discharge is 1,200. But in China, like Chinese people, we discharge the total carbon dioxide is 150, almost 8 times different. Do you think, we are now facing the same goal to try to reduce, to try to perform the carbon neutralizations? Do you think the developed countries that have the responsibility to help the developing country or per country to perform the same goal, 2060, 2050?
I think that and I think the United Nations recognizes also that the developed countries have a responsibility to act and the developing countries have a responsibility to act later as they develop a better life for their people. So I think in that respect, we've got it about right. China has said that they will peak their emissions by 2030. That's only 8 years away. And I think it may even be sooner, because I believe that the Chinese government thinks that there indeed is prosperity associated with making this transition. So my hope is it'll go even sooner, but even according to the United Nations and the plan, the developed countries should go first.
Thank you. We hope to, get technical support from the developed country, because for Chinese people, for China government, we have a very limited time to perform the carbon neutralizations. We only have like 30 years, 40 years. So this is very hard for us.
I understand.
Because we need renewable energy. This is maybe the first priority to perform the carbon neutralizations.
Thank you.
Thank you. We have one question in the chat box from Dr. Henry He. He asked, if electrify everything instantly, currently, do we have enough knowledge and ability to handle the various issues associated with the solar panels, such as waste, decommissioning, vast amount of discharge of trace elements?
Another great question. Thank you. We talk about the students' circular economy, right? A circular economy. But in a circular economy, would we have allowed Tesla and the other electric car manufacturers? They don't recycle now. It's almost 50% now, but they don't recycle the lithium-ion batteries, more than 2,000 in each and every Tesla. Should we have allowed that production before we knew how to recycle it? That's a legitimate question, I think. Or in my country, the wind turbines, the blades of the wind turbines, we don't know how to recycle them. Just now, they're becoming to become outmoded, and they need to be recycled. So I think we need to be able to have this idea of a circular economy at the beginning, even before we license a new product. Now, the whole interesting with the hybrid vehicles, the nickel metal hydride batteries, they are being recycled, and almost totally. But the lithium ion batteries, at the end of their life, they have about 70% charge capacity left. 70% charge capacity is not enough to run an automobile, but 70% charge capacity is enough to make battery storage at a wind farm or a solar panel, solar photovoltaic installation. So we need to complete that cycle. We need to recycle all the lithium ion batteries. We should have had a plan even in the beginning for that. And that, I think, would help to address this gentleman's question.
That is a very important recycling. Now, may I invite Professor Noaa to give some comments and questions?
Thanks, Kenneth. Thanks, Kenneth, and then thanks, Jerry, for so inspiring talk this morning. And I'm very glad that you're so optimistic on our future on climate change and sea level changes, because I think we have discussed this topic for many, many years. As scientists and academics, we believe this is important. We have done a lot on that. But if you look at the real situation as a layman or general publics or young citizens, they will see that we didn't have much progress. The situation seems worse according to all the scenarios, the predictions. So I think we need to stimulate all these young people or laymen to follow our idea and understand the situation, how serious. And I think what you say is like only 7 years we can burn our fossil fuels, otherwise it will be nothing there. All this message, I think we need to translate it to simple layman terms. And so our citizens and our non-academics or not political scientists, I think political scientists, they believe that it's a serious problem. So I think our role is to how to let the laymen and citizens, which are the majority, to understand that we are doing something, we still have the chances, and so on and so forth. I've been thinking about that, but I cannot see the way move forward and translate our knowledge on that. Will you mind to give some insight, because you are more optimistic than me, to help the others, and as scientists, what can we do more to promote this kind of optimistic views and more positive atmosphere among us on this topic? Thank you, Jerald.
Thank you, Noaa. That's a great question. I wish I knew the answer to that question, but I will say that it's remarkable that the young people, at least at our university, they really realize it's a serious problem, and they want to act, and they are acting. For example, I have a class right now, about half of the students are vegetarians. I was surprised, and when I asked them why, they said because of this impact on the environment. It surprised me very much. Another thing which surprised me, Noaa, is that they don't blame us, the older generation, leaving them, with a kind of planet in bad shape, and they don't seem to blame us. And sometimes I think I don't understand that, because as you said, we've been talking, the first United Nations meeting was in 1972. And Gro Brundtland, the Prime Minister of Norway, did Our Common Future in 1987. And so we've known about this for a long time. And while we have made progress, and while there is hope, it hasn't been fast enough, as you say. And it's going to get worse before it gets better. I'm sorry to say, but in the end, I'm convinced this is the way to the future, and that we will eventually recognize that, if not our generation, then the next one and the next one. That's my hope.
Okay, thank you, Jerald. I hope SKLMP and all this kind of organization can help to promote the message or rouse everybody's interest back to this topic and be as optimistic as Jerald, so that we have a better future for our young generation. Because there's a Chinese saying that in Chinese it says 记忆很难. That means in English, you know something, you have the knowledge, but it's difficult to translate it into behavior or actions. And that's more like it in the Asian countries, that they always say, I know it, I know the problem, you don't have to tell me. But when it comes to the real situation, they don't translate it into behavior or action. That's something we worry about our people, at least in this part of the world, that they are always saying that I know it, you don't have to tell me. That's the problem I can see. So I hope we can do more on that. Thank you, Jerald, very much.
Thank you. You need to say it one more time for me. I need to learn that saying.
Okay, that means you know you have the knowledge, you know what's going on, but you do not translate it into action or behavior. So it's not like your student, they will say, I will be vegetarian because it will help to protect our earth and to reduce the carbon dioxide emission. But on this side, I can see my students, most of them, they know, yeah, we should do it. But when you ask them to do it, they will be hesitate, and they will have a lot of reasons not doing it. That's something I see the difference. I hope we can change this trend, and that's what I really want. We can help our Earth in the long time periods.
Thank you.
Thank
Thank you, Professor Tang. And now we still have 5 minutes. May I invite the students, young scientists, to ask questions? Maybe the first one from Ms. Fia Bedford. Fia, are you here? And also Wingbo Learn. We have a question from Yali Wang. She said, I'm interested in justice. We already know there is a carbon leakage. That means climate policy of one area may have adverse impact on other areas. How can we solve this problem, or what kind of knowledge do we need to solve this problem? Climate justice.
Climate justice has to do with equity and fairness. And of course, as long as we have these problems, they're visited most seriously on the people who did the least to cause the problem. And that's the farthest thing away from justice. And I sympathize with the questioner, but it is a major problem at all of the United Nations meetings because for example, there's, I believe, 43 countries which have been identified as most vulnerable. They're mainly island nations, coastal nations, poorer countries, agricultural countries suffering drought. And these 43 nations, if you look at their collective emissions, it's almost zero. So again, they've done the least to cause the problem, and they are suffering the most, sometimes even having to abandon their homes and habitats. So there is no justice. We have to work towards justice, and that's a part of the reason why, even though I'm just a professor, I try to attend these meetings and make a small difference as much as possible.
We also have a young scientist here, Dr. Chen Jinlin. Maybe better you speak on your own, by yourself. Dr. Chen, please. Dr. Chen, you can unmute. Yes, please.
Yes, I'm here. Yeah. So thank you, Jerry. Yeah, my question is that there's another opinion among academics that if we look back at the human history and seeing like the tens of the thousands or even millions of the year, it was not uncommon for the carbon dioxide concentration on this planet and to be several or even 10 times higher than it is now. Okay, but the human and other creatures have survived. So why is the carbon dioxide a problem for our human being now? And isn't this an evolutionary question? So what do you think about this opinion? Thank you.
Thank you, Professor Chen. You know, humans have only evolved from, there were 3 species, Homo erectus, Homo habilis, and Homo sapien. Homo sapien only has been around for about 200,000 years. So in that 200,000 years, it's never been like this. Never so high carbon dioxide, never so high temperature, never so high other greenhouse gases. One has to go back to the Pliocene 50 million years ago in order to find carbon dioxide concentrations clearly larger than now. And it's only in the last, at that time, the continents still were not in the place where they are now. So the energy balance was much different on Earth. And the exposed microbes, soil, and loss of ice was much different than it is now. The energy balance of the Earth now, in addition to being affected by greenhouse gases, is affected by Jupiter and Saturn. The irregular orbits of Jupiter and Saturn have a strong gravitational pull on the orbit of Earth. And we have three kinds of eccentricities: the wobble or precession, like a top of our Earth, the angle with which we present ourselves to the sun, 23.5 degrees, and our orbit, the epigee and the perigee. When that changes, we go into and out of ice ages because of a change in the energy balance. But what we're doing now, Professor Chen, is much different than has ever happened in human history, the 200,000 years of Homo sapiens. We've never had where we're adding so much carbon dioxide, the temperature, we're waiting for in English, we say we're waiting for the other shoe to drop. The carbon dioxide is very high. We're waiting for the temperature to increase to accommodate it. Always before the energy balance of the Earth changes first, and then the carbon dioxide changes due to the change in the energy balance. So what we're doing has never been done before. Humans have never experienced what we're experiencing now.
Jerry, we have the last question from Dr. I don't know how to pronounce the name, SAIF and UDTIN, Andy. Would you like to speak up by yourself, or I read out the question for you, Dr. Andy?
Hello.
Yes, please.
I am PhD student, not doctorate. My question is to the professor. It was a nice presentation. I am from Bangladesh. It's a low-income country. So my question is that due to the development works, we can understand that climate change is happening everywhere. And we are connected in the world, everyone. But in the low-income countries, there are a very low number of research. So how developed country can extend their research to those countries? How they can work with them? What is your suggestion regarding this?
Thank you, Dr. Udin. I think that there has to be transfer payments, and transfers of knowledge and patents from the developed countries to the developing countries like Bangladesh. And Bangladesh certainly has many claims, once again, very few emissions and very great change in monsoon and changes in the Himalayan glacier melt. So Bangladesh is much affected through very little fault of your country. So there has to be assistance technologically and research, as you said, from the developed world to Bangladesh and other countries. And I hope those are ongoing as a result of the Glasgow and other negotiations. They need to be. There's $100 billion a year, which is supposed to go to the most vulnerable countries. Bangladesh is one of them, and the 43 most vulnerable nations. And only this year are we close to raising the $100 billion from the rich countries. Now, that's not research. That's something different than you asked about. But also transfer payments have to occur as well. There's been damages in Bangladesh, and there should be damages paid by those most responsible, like my country.
Thank you.
Very good. So now may I finally invite another tiger to ask you a question or give a final comment. Dr. Leo Chen, please.
Yeah, Jerry, thank you for your inspiring and informative talk. Since we are tiger, so I am as optimistic as you. And I believe only rely on scientists is not enough. So we need to outreach the citizen scientists, like the young generation, and as Laura say, easier said than done, right? So we may need to change our lifestyle in the daily life. As you say, reduce the meat, but maybe we cannot reduce the beef, but we can plant more trees and use the electrical car. And in the past years, I tried to bring young generation into the sea by scuba diving training. So I believe seeing is believing. So they will understand how worse, like the ghost there, the rubbish they can see in the coral reef damage the coral. And then they will love the ocean. And recently, I also developed some kind of I call the nature photography. So use photo to protect the biodiversity. So I think people like to see the beauty of the nature. Then they will fall into love with the nature. I think we need to spend more time to translate scientific research into general education. So as you say, we also are work with the NGO to plant the mangrove seedling. So I think this kind of action, I think scientists, they need money, they need resources, but the citizen scientists, they are volunteer to protect the environment. I think this is a huge resources to protect our nature. So I'm very optimistic. I think if we can put more efforts into education, we have hope for the planet. And also, I think you may not realize the Hong Kong coral is a very tough coral. The Hong Kong coral can survive from 13 degrees to 30 degrees. So wow. Even under the future climate change, maybe the Hong Kong coral will be the future coral. So if this is another important point, we may need to protect the Hong Kong coral for the future. And as you say, the ice melt will change the salinity. The Hong Kong coral also can survive under a wide variation of salinity change. So I think this kind of things, I think we need to bring global attention and I think joint effort to protect our blue planet. So also I think your talk is very alarming. As you say, the 8 nuclear pump release the heat every second. I think this kind, I need to learn this kind of technique to teach my students. So then they will see how serious of the climate change problem to our future. Yeah, thank you, Jerry. Yeah. Yeah. So I hope you can go to Hong Kong and then foot massage.
I hope I can. Thank you, Leo, who showed me all the best foot massage places in Hong Kong. As tiger to another tiger, I have great respect for what you're doing and showing other citizen scientists by scuba diving, by planting mangroves, and I respect that very much. Thank you, Leo Chan.
Thank you, Jerry.
Thank you, Jerry. Now we hand over back to Phoebe.
Okay, thank you. And we still may have many questions here, but time is up. So I have to skip to the end. So we are very hearty gratitude to Professor Schnoor for giving us the wonderful speech today. And we expect more opportunities to communicate with Professor Schnoor. So thanks to all the participants for attending this lecture. And I also would like to thank Professor Leung for giving Professor Schnoor here. Thank SKLMP for launching this distinguished lecture. And also thank the Department of Chemistry to help organize these events. And thank all of you for your time and active participation. We look forward to meeting you again in the next distinguished lecture with Dr. Janice Stapa. Okay. And that's all for today.
Yeah, thank you, Jerry.
Thank you again.
Thank you, Phoebe.
Okay, bye-bye.
Thank you, Kenny. Thanks to everybody, all my friends.